Good day to Dr. Stephen. My name is Anjamin from Group Life of Givings. I'm here to discuss about the application of MATLAB on solving optimization problems. Equation below shows the chemical reaction between methane and steam, which known as steam methane reforming. Steam methane reforming is a major technology to produce hydrogen, and its byproduct is carbon dioxide or carbon monoxide, depends on which reaction it carries on. It is the most conventional and cost-effective method to produce hydrogen gas in a large scale by feeding in hydrocarbons, steams, and heat to the reactor system. The objective of this study is to find out the reaction temperature that yield the most hydrogen in steam reforming of methane. This is the objective function of the optimization problems, which is subjected to one bound constraint. The objective function was to maximize the yield of product, which will affected by the reaction temperature. And we got to find the optimized reaction temperature between 600 to 1100 Kelvin. Now we move on to the script file. We provided three script files inside the submitted folder. The first file will be q2b computation.m file. We will compute the thermodynamic information needed before we proceed for the optimization. This file is to compute the thermodynamic data such as Gibbs energy, heat enthalpy, equilibrium constant, extent of reaction, and yield. This file we also use to plot the graph of yield versus temperature. Then with the graph plotted, we will generate the objective function with the aid of Microsoft Excel. The objective function will be keyed into the q2b objective.m file. Lastly, q2b.m file is to set up the optimization problem with an initial gas value. The optimization problem will be solved using this file by calling out the function of q2b objective.m file. Then, the result will be presented using a table inside the file. So basically, this is the q2b computation.m file. And the first, we need to clear the previous input so that we could ensure our outcome will always be accurate. And next, we gotta set P at 1, as we gotta fix the pressure at atmospheric pressure for the following computation. This section is to store the thermodynamic data. You can see that we store the thermodynamic constant A, B, C, D, as well as the heat enthalpy, Gibbs energy, the stoichiometric coefficient for reaction 1 and reaction 2 in the terms of matrix. The sequence of each data were stored according to the sequence of each component listed over here. So the following section is to compute the summation of the thermodynamic data that listed in the above section for each reaction. We also need to calculate the equilibrium constant at 298 Kelvin for both reactions. And then we're going to set a new array so that we could store the equilibrium constant of each reaction at different temperature. Next, we gotta calculate the equilibrium constant at different temperature. We utilize for loop for the computation, which starting from 600 Kelvin to 1100 Kelvin with an interval of 100 Kelvin. The equation of equilibrium constant was shown in the right corner of the screen. In each loop, the calculated value will be stored in the array K1T and K2T created in the previous session. The value of each loop at different temperature could be viewed over here. And obviously, this will be 600, 700, 800 Kelvin, and so on. The same goes to K2T. And finally, we could calculate the extent of reaction as well as product yield. The procedure to calculate the extent of reaction is exactly the same with what we do for equilibrium constant. But the only thing different over here is the F-sub function. The F-sub function is used to compute the nonlinear equations by setting the initial point at 0, 0. The epsilons will be stored in a 6 times 2 matrix as shown here. And this will be the epsilon for reaction 1 and this will be the epsilon for reaction 2. With this epsilon, we could calculate the product yield easily. With the calculated product yield, we could finally plot the product yield versus temperature graph. And from the graph, we could see that the maximum product yield was around 1000 Kelvin over here, but we couldn't tell the specific value of the temperature. Therefore, we need the help from Microsoft Excel. Importing the data from MATLAB into Microsoft Excel, we could plot this graph again, and with the aid of the trend line, we could get the equation of the smooth curve. This equation will then be the objective function of our optimization problem that's going to be used later. The objective function will then be keyed into Q2B objective, and then it will be used in Q2B.m file. As you could see, there's actually a negative over the objective function. This is to maximize the objective function instead of minimize in the MATLAB. And inside the Q2B file, we gotta solve the optimization problem. Firstly, we set the initial point at 1000 Kelvin, as we could know from the graph generated before that the maximum point was around 1000 Kelvin, and therefore we are setting it as our initial point. After that, we gotta set up the maximization problem and also call out the fmincolumn function to compute the nonlinear objective function. Then the Q2B objective will be called out, as well as the initial point and the lower boundary 600 and upper boundary 1100. Then the result will be shown over here. By calling out the Q2B file, we could finally get the optimized solution. The solution was computed at 9th iteration, and the optimized product yield is 0.5794 or 57.94%, which corresponds to the temperature of 1010 Kelvin. This product yield is included the byproduct, which is the overall product yield, and this could tell us that to get the maximum product, the reaction needs to be run at a temperature of 1010 Kelvin.